All right, we finished through all things brand new content for this quarter in this year. Today you're going to spend just a little bit doing a couple applications related to sector area and arc length. So I just wanted to walk through a couple examples, and hopefully these help you as you tackle the applications you're doing today. Again, you probably want to have your notes handy so that you have those equations for arc length and sector area. And then you just want to make sure that you're kind of walking through these 3 steps. These are what we've practiced when we've done applications, when we did them with trig and other things. So I'll just kind of remind you. Step 1, draw a diagram. So you just kind of make sense of what's going on and then label it with the given information. Okay, so step 1, try to make sense of that problem. Then step 2, what are you being asked to look for? So is this more of an arc length? Are we finding a piece of the circumference on the outside? Or is it asking us for area on the inside? And then lastly, you do need to, again, use those formulas, choose the correct one, and then make sure when you get to the end that your answer makes sense. Okay, those are the steps we're going to go through. So just 3 examples in this video. Example 1 says a 6-foot pendulum, and I've given you a little diagram of what a pendulum is, in case you didn't know. It just swings back and forth. It's going to swing through an angle of 12 degrees. So again, our drawing doesn't need to be exactly accurate like those crazy trees we drew. But if this guy's going to swing right through 12 degrees, essentially he's going to be over here now, and this is like 12 degrees. Now that's much bigger, but let's call that 12 degrees. Find the length of the arc. So it looks like we are finding this length right here, through which the tip of the pendulum swings, okay, during that time. So we're finding this length right here. Now again, remember, if we look back at our formulas, in this case, it's asking us to find arc length, okay? So we've got a diagram making sense of that. We didn't label yet the length, right? We need the length of this pendulum. It looks like it's a 6-foot pendulum. So this radius is 6 feet. Now, why is it the radius? Well, notice if this is like the center that it's spinning around, we wouldn't necessarily draw this all the way around, but notice if we were to draw that pendulum swinging clear in a circle, it's going to create a circle, and that little pendulum is simply the radius of that circle. Okay, so we don't necessarily need to draw the whole circle, but understand that's the radius. So arc length here, again, is a piece of the circumference. So remember, circumference was 2 pi r, and then we only want a fraction of the circumference, so we take our angle, whatever that is, and we divide it by 360 degrees. Okay, so this is what we're looking for here. So we just plug in our information. So we're going to say, well, it's going to be equal to 2 pi times the radius. In this case, our radius is 6 feet. Oops, I accidentally erased that. And then we multiply that by our angle measure. So the central angle is 12, and that's going to be over 360 degrees. And then hopefully you guys are getting really good at plugging these in the calculator. So we've got 2 times pi, right, times 6, and then we times it by that fraction. So sometimes I just do times 12 divided by 360, and it looks like it's swinging through about 1.3 feet. Okay, and again, we look back to make sure that that makes sense, right? If that's a 6-foot pendulum, it's not swinging very far with that 12 degrees, so that seems like it's about right. All right, that's arc length. Example 2 says a center pivot irrigation system consists of 400 meters of sprinkler equipment. Okay, again, that central pivot irrigation system, that's what we talked about before when you have a circular field, and I'm going to draw a circle right here. And it looks like they have sprinklers that hook at the center, right, and then they go out, and it's telling us it's 400 meters of equipment here, and then that rotates all the way around the field to water the whole field. And it says that it's moving at a rate of once every 3 days to irrigate the circular region. So it takes 3 days to get all the way around that circle so that they let it soak good. And it has a diameter of 800 meters, so that would make sense there, right? That's 400 meter radius, or again, diameter of 800. Find the area to the nearest tenths, so 1 decimal place, of the sector that is irrigated in 1 day. Okay, so again, we're finding sector area on this one. So I would say, okay, well, I'm finding sector area, and sector area was pi r squared, and then again it was times that fraction of the circle that I want to find. Now this one doesn't give me a central angle, so what would I do at that point, right? But remember, it tells me that it takes 3 days to get all the way around. So how far would it get in 1 day? Well, it would go a third, right, every day. So the first day it would make it a third of the way around, the next day another third of the way around, and then in 3 days it's going to make it all the way. So essentially we're finding a sector right here, and it's going to be a third. So we could find that angle measure, or again we could just say a third of the area, and the area is pi r squared. Our radius is 400 in this case. So we're looking at something like this, right? So we're going to take 400 and we're going to square that, and we're multiplying that by pi. And we only want a third of that. So in this case, we're looking at 167,551.6 square meters. So again, finding the sector area on example 2. Last one, example 3. Find the area of the shaded portion of the figure. This is similar to something you would see on an ACT, just using basic area formulas. But what they're trying to portray is that oftentimes you'll notice this shaded area, looks pretty complicated. Those aren't shapes that we know how to find the area of, but we know how to find the area of a rectangle, and this whole thing, right, is just a rectangle, length times width. And we know how to find the area of circles. So if we can find the area of the whole rectangle and then just subtract out these pieces that are not shaded, we can actually come up with just leaving the shaded. So again, you want to find the area, right, of the whole shape, and then you're going to subtract out the unshaded pieces. Okay, so the area of the whole shape, again, this is the area of like the rectangle. Okay, so the area of the rectangle is length times width. So it doesn't necessarily label that for us, but notice that the radius of this circle right here is 3, which means that the radius of the circle right here is also 3. Radius right here is also 3. So we know that the height of this rectangle is 3 plus 3, right? It's going to be 6. So we're going to do length times width, or in other words, height times, right, the length down here. So that one's 6. And then notice these are also moving in little increments of 3. So that's 3. Half that circle's 3. Half that circle's 3. Half that circle's 3. So this one, right, the length down here is going to be 3 plus 3 plus 3 plus 3, which is 12. So the rectangle is length times width. So in total, it looks like our rectangle has an area of 72 square units. They didn't give us units, so we'll just write U. Now we want to subtract out the circle pieces. So notice we have a full circle on the inside, right? And we want to subtract out that. But notice on the outside you have a half a circle on the right and you have a half a circle on the left. So really that would make a full circle. And then you have a full circle in the middle. So really you're just subtracting out 2 of those circles, right? So I'm going to take this and say, well, 2 of these, and then let's find the area of the circle. So we're going to say pi r squared. That's a 3 squared, right? And then let's go ahead and approximate that. So we've got 2, right, times the pi times 3 squared, and it looks like that's about 56.5 square units. So again, if I want to find the area of the shaded region, so the area of the shaded is just the total, or the big rectangle, subtracting out those circles on the inside. Okay, and when we subtract that out, that leaves us with just the shaded piece, which is about 15.5 square units. Okay, 3 different kinds there, so make sure that you kind of draw your diagram. Are you looking for arc length or sector area? Once you've made that decision, choose the correct formula. And then when we get down to these shaded portions, we're just practicing seeing it as a whole and then subtracting out areas of inside figures that are unshaded.